This narrated PowerPoint focuses on binary stars and the use of Kepler's third law to find the masses of the two stars in that system. So here we have a close-up of the part of the formula sheet, which is the new formulas for this exam. You see here Kepler's third law. The M's stand for the masses of the two stars. We'll call one M1 and the other M2. It doesn't matter which one's which. We have the period of the orbit, P. Notice that it's squared. And we have the average distance between the two, or the average separation between the two stars as they orbit each other. And notice that that is cubed. Also notice the cautionary note that it must be in solar system units. You really have to be careful of the units in one of these Kepler's third law problems. So what do we mean by solar system units? Both of the masses must be in solar units. A must be in astronomical units, AUs. And P, the period, must be in years, good old Earth years. Now we still are going to have two variables here because there are two stars. And if you only have one equation and you have two variables, you don't have enough information. So we need to be given additional information in the problem itself. We need to know the relative masses of the two stars. For example, is one star twice the mass of the other? Is one star 4 times the mass of the other? Are they the same mass? We need that information in order to solve this. Once you have that relationship between the masses of the two stars, you then substitute in this relationship for one of the star's masses and then solve for the other one. So, here's Kepler's third law. A typical problem might be as follows. If two stars are the same mass and orbit an average of 6 AUs away from each other with a period of 10 years, what are the individual masses of the stars? So what do we know? Well, we don't know what the masses are because that's what we're trying to solve here. So we have M1 plus M2. We have to multiply that by P squared. P is 10 years. That is in the correct units. So we just multiply that by 10 squared. Then we need to know the average distance between them. The average separation is 6 AUs. That is also in the correct unit. And so we have over here 6 cubed. Now 6 cubed is going to give me, over on the right-hand side, 216. 10 squared is 100. So M1 plus M2 times 100 equals 216. So what am I going to do now? I'm going to divide both sides by 100. If I divide both sides by 100, it cancels over here, and on this side we get 2.16. So I know that the combination of those two stars' masses, M1 plus M2, is 2.16. But I want the masses of the individual stars, not the total. So here is where I have to have more information. And it says that if the two stars have the same mass. So if they have the same mass, I can say that M1 equals M2. So I can substitute in here M2 plus M2 equals 2.16. So it's like saying 2 M2s equal 2.16. So it's like 2 bananas weigh 2.16 pounds. So how much does each banana weigh? Well, obviously, we divide both sides by 2, and we get that M2 is going to be 1.08. 1.08 what? 1.08 solar masses. What's the mass of the other star? Well, we said that they're the same mass. So the mass of the first star is also exactly 1.08 solar masses. Here's a problem which is a little more challenging because the stars have different masses. So we're given that the period is 25 years. That is in the right units. We're given that the two stars have an average separation of 17 AU. That's also in the right units. And we're given that one star is twice the mass of the other. That's the other piece of information that we're going to need at the end. So M1 plus M2 times P squared. So this is going to be times 25 squared is going to be equal to A cubed, 17 cubed. So M1 plus M2, 25 squared is 625. 17 cubed is 4,913. So how do we get these masses over here by themselves? We have to divide both sides by 625. If we do that, then the 625s cancel. So M1 plus M2 is equal to, drum roll please, 7.86-ish. All right, so that's the total mass of the stars. But we're not done because we want to know the individual masses of the stars. So now we need this piece of information. One of the stars is twice the mass of the other. Does it matter which star we claim is twice as heavy? Absolutely not. Doesn't matter. So I can say that M1 is twice the mass of M2. And then I can go back and substitute that into here. So instead of writing M1, I'm going to write 2 M2s plus M2 equals 7.86 solar masses. So 2 bananas plus 1 banana is 3 bananas. So this is going to be 3M2 equals 2.86 solar masses. So now I divide both sides by 3, and I get that M2 is equal to 2.62 solar masses. Now, how do I get to M1? Well, I know that M1 is twice as heavy as M2. So I can take 2.62, multiply that by 2, and I get 5.24, and that is going to be equal to M1.